One of the applications of Liouville's theorem is the fundamental theorem of algebra, which states that any polynomial has at least one zero. More precisely, if we have a polynomial of the form a0 plus a1 set plus a2 set square plus and so on to an set to the power of n, where a1, a0, a2 and so on are constants, and we assume that an is separate from 0 and that n is larger than 1, but an integer larger than 1, of course. So any kind of polynomials of this type has at least one zero. That means any polynomial at all. This implies that any polynomial of this of order n can be written in the following form: p of z equal to some constant c multiplied with z minus z0, the first zero of the polynomial, z minus z1, the second zero of this polynomial, and so on to z minus zn, where zn is the nth zero of the polynomial. Many of these zeros may be equal, but when we are saying that it has n zeros, we are counting multiplicities. What does that mean? Without going into detail, I think you will understand what I mean by considering the following example. Z minus 1 to the power of 5 can be written as the following product. We have 5 products, and what we are saying is that 1 is a zero of this function with multiplicity 5. So in this way of counting zeros, we obtain that any polynomial of order n has n zeros. We have another result, which is we are going to use in exercises, and you will maybe observe this on the exam. It states the following. It's called Rouches theorem. We let f and g be analytic functions which on an interior to a simple closed contour C, and we assume that the absolute value of f is larger than the absolute value of g for all sets on this contour. Then the function f of z, which has larger absolute value, has the same number of zeros interior to z as the sum of these two functions. And again, we are counting multiplicities. In order to understand this theorem and the application of it, we consider the following example. Here is some contour C generally, and let's for simplicity consider the circle at center 0 and with radius equal to 1. And let h of z be the following analytic function. You see that this must be analytic because it's a polynomial, and the polynomial can always be differentiated. So we want to find the number of zeros interior to C. This is not so easy to do without computers because it's you have a polynomial of 7 degrees, so there are no general formula for finding the zeros. So, but we are not interested in the zeros. We are interested in how many zeros are inside this circle. So what we are doing here is that we are dividing the function into some f and some g. It's not easy to before we start with the task to be sure whether we should call this f of z or this f of z or some other part of the function f of z, but we have to try and fail, and in this way we find it. But okay, if we choose now f of z equal to be this part of h of z, then h of z is the sum of these two functions, and this function is rather easy to find the number of zeros inside the circles, because it must be 3. All 3 zeros of this function are placed at the center of the circle, namely in the origin, and they have multiplicity 3 because this is a third order polynomial. But let us now check the absolute value of this function. It's the absolute value of minus 4z squared is equal to 4 absolute value of z to the power of 3, and we know that absolute value of z here is equal to 1 on the circle, so we know that f of z is equal to 4 for every z on the circle. Let's consider the absolute value of g of z. G of z is this function. We are then using the either the triangle inequality or the reversed triangle inequality, as we have used several times before. The absolute value of g of z is using the triangle inequality. We obtain that it's the absolute value of the first component, the first term, plus the absolute value of the second term, plus the absolute value of the third term. And we obtain that this is equal to the absolute value of z to the power of 7 plus the absolute value of z plus the absolute value of 1. And noting that we are on the circle, the absolute value of z is equal to 1, so we can insert 1 instead of z here, absolute value of z. Then we obtain 1 plus 1 plus 1 equal to 3. So we know that g of z is less than 3, which is of course less than 4. So what we can conclude is that 4 must be larger than g of z on all points of this circle. And then by Rouches' theorem, the number of zeros of the sum of this function h of z must be equal to the number of zeros of the function with largest absolute value, namely f of z, which had 3 zeros inside the circle. And we conclude that there are 3 zeros of this function h of z counting multiplicities. We don't know where they are, but we know they are inside the circle.